I really don't have any big announcements other than just make sure you get your minutes in. And again, I'll let you all set the pace. After we finish dead loads and live loads, I'm thinking we're already done with dead loads, but once we finish live loads, I think we're going to kind of get to a point where what we talk about and what we cover versus what I need to tell you. Do you see what I mean? In other words, I mean, by the time I finish live loads, I mean, September will be over. You know, your alternatives report is due in October. So I don't want to say I'm going to come in and just let you all tell me what to talk about, but there will be sort of a point where, you know, I don't want to spend, like, let's talk about lecture. You know, once we finish loads, you know, from a structural engineering standpoint, you get into resistances. And resistances are going to be a function, here, let me adjust the lights. Resistances are going to be a function of whether you do a steel bridge or a concrete bridge or whatever. And what I don't want to do is just say, okay, well, I'm just going to talk about steel bridges or I'm just going to talk about concrete bridges if some of you all are working on different alternatives. So I do want you all to start thinking about, okay, what actually do we need to be talking about in class in order to be moving forward, okay? So that's where, I mean, we're starting to get to a point where instead of me coming in and organizing the class, it's you coming in and organizing the project. See what I mean? So it's something you need to think about, you know, talking about what you need to cover. And honestly, if we come in and you all are just rocking and rolling with your project and just trucking along and you don't need to meet, I mean, we can even discuss that. I don't have a problem with that. Just know, I mean, when it comes to deliverable time, once we, you know, our deliverable time is set in stone, it's set in stone. So just something to keep in mind, okay? Any questions? So what I want to do is I want to go through some calculations on live loads, and specifically I want to talk about the live load distribution factors. It's a little long, it's a little bit of a lengthy process, but I think you're going to find that it's pretty rote and pretty straightforward. I think if you were to pull this, you know, from some online resource and just sort of look at what they're doing, I think it would be a little confusing. So walking through some of these calcs, I think, is pretty valuable. So let me go back to a little bit of an earlier lecture. Let's look at this one. Okay. Now, I've been using this example as a sort of some fundamental basic calcs that we've been doing throughout the beginning of the semester, and I'm still going to use that for the, this live load assessment. And specifically what we're going to do is we're going to compute live load distribution factors. Okay. This is a very nice example for doing that. I don't think it would matter if you're using a steel bridge or a concrete bridge or what have you. You would literally be just looking at different equations, but they would all be from the same location in the spec. And a lot of the parameters and the variables that go into it are identical. So as long as you know how to go through some basic live load distribution factor calcs, I think you'll be able to handle just about any bridge that you decide to assess. So let's go through a couple things just to make sure everybody's clear on some of the parameters that we're going to use. So here's our bridge. Let's just keep this straightforward. What's our girder spacing? 10 feet, okay. Our overhang width, our overhang is defined as from the center of the exterior beam to the edge. So that's 3'6". Everybody see that? Okay, or 42 inches. Now, our barrier is 18 inches wide, or 1'6" wide. That's going to matter when we start looking at exterior girder calcs. Lastly, our slab thickness, are we going to use 8.5 or are we going to use 8? Well, that's an interesting dilemma here. The answer is actually 8, and here's the reason why. When we compute distribution factors, one of the parameters that affects live load distribution factors is the stiffness of the bridge. In other words, the higher the stiffness, or if your stiffness changes, you're going to get a different live load distribution factor. Specifically, the higher the stiffness, the higher the distribution factor. So because we're looking at stiffness, we're actually only going to use the 8 inches because we're not going to actually account for that from a load standpoint. We've kind of already done that when we did our dead load. So just a nifty point to bring up. Yes?
So the 8.5 is only, we only use it for the dead load.
For the dead loads. Yeah. What were you saying though? Oh. No, that's fine. All right. Now our span length, what we're going to use for span length is 90 feet. Okay. Now for your bridge, you can just use a different span length, but I think you'll see it's just literally changing one number. Okay. Everybody okay with this? All right. So let's just go ahead and do some basic example calcs. So we'll say, okay, so some parameters. So S is our girder spacing, and we always report that in feet, so the value that we use is 10. L is our span length, which we always report that in feet, so that's 90. Okay. Slab thickness, we say is 8 inches, and we always report that in inches. Now, one of the first things that we're going to have to compute is what's called a longitudinal stiffness parameter. Okay. And that is kg. Now, the way that we compute that is we say it's the modular ratio times the quantity A plus A EG squared. And we covered that in our last lecture, right? Didn't we mention that? Okay. All right. So help me out. Let's see if you all remember this. What is our modular ratio going to be for this bridge? Does anybody remember this? Steel bridge, concrete deck? 8. 8. Okay. Next thing we need is a moment of inertia. Okay? Now the moment of inertia is the moment of inertia for just the steel by itself, which what I did was this, is I pulled this up. Remember this? Remember this calculation that we did together? Where we looked at the shapes and the top flange, web, bottom flange, and went and did our moment of inertia. Now the numbers I want to call to your attention are this and this. So let me take this moment of inertia. Let me switch it down a little bit. So our moment of inertia for the steel beam by itself was about 16,000 inches to the fourth. Everybody remember that? And our area is about 48.88 square inches. So what I'm going to do is I'm going to say 15,969 inches to the fourth. And our area is for the steel only. And that is 48.88 square inches. Again, if you've got this set up in Excel, I mean, you can have it automatically reference all the values. So I can guarantee you that what we do by hand and what you would do in Excel would be a little different. Everybody okay with this? Okay. Now, EG takes a little bit of explanation. Okay. It's not that hard. It's just something to think about. Okay, so okay. Now, first thing I want to look at is this. Okay? I want to look at Y bar. Now I want to look at Y bar for just the steel beam by itself. Okay? Now how would I compute that? Well, I go to my spreadsheet, and I've kind of already got that computed here. Remember, it's just sum of AY over sum of A. Remember that? So if I take those and divide that out, I get about 17.99 inches. Everybody okay with that? So we'll say this is 17.99 inches. Okay. The next thing I want to compute is this. Okay. Now specifically what this is the distance from the bottom of the girder to the center of the deck. Okay? So tell me, how do I compute this? What do I add? I add, okay, hold on. Now you're saying y bar times 2. You're assuming that the girder is symmetric. It's not. Okay? The bottom flange was bigger than the top flange, so y bar times 2 won't get you all the way to the top. Okay? Let's just think about this from a dimension standpoint. If I start here, how do I get from here to here? Thickness of the bottom flange, right? Depth of the web, the haunch, right? Because the haunch already includes that, and then half that. Make sense? So I propose you take the thickness of your bottom flange, you add the depth, you add the haunch, and you add half the slab thickness. Okay? So what do we get? That plus that plus that plus that divided by 2. 49.25. Everybody okay with that? So far so good? Okay. If you're okay with that, then I propose that this distance right here, this is EG. So how am I going to compute EG? Just the difference of those two, right? And what is that? It's too early for me as well. About 32, 26. Did I do that right? $31.26. Dang it. I was close. My caffeine hasn't kicked in either. So, therefore, EG is 31.26. So if you've got all these, kg equals 8 times 15,969 plus 48.88, that's inches, times 31.26 inches squared. Now, don't worry, it comes out big. kg is a really big number. Yes? We used 8. Because what we're that's it's a good question, and it might seem a little odd, but what we are doing is we're essentially trying to compute the stiffness of the girder. So we're underestimating. We're using the 8, not the 8.5, because the stiffness affects what the live load distribution is. It's a good question, though. I mean, it's probably, you know, like 600, 700,000 or something. It's big. So 31.26 is squared. $509,871. We'll just. That's good enough for government work. Do I have a second on that? Okay. So don't be freaked out if you get a big number. You're especially going to get a big number when you're looking at steel bridges. See, when the study was originally done to come up with a lot of the equations that are in the spec that we use nowadays, see how we're multiplying this whole thing by 8? Everybody see how we're doing that? The reason why we're doing that is because the original study back in the 80s that was done, they used a generalized computer model. This was back in the 80s. We didn't, have the computational technology we do now. So they used a generalized analysis model to do all their studies. And in their analysis model, it essentially assumed everything was concrete. So if you've got a steel bridge, what you've got to do is you've got to compute an effective concrete stiffness. That's kind of what we're doing here with this kg term. When you get 509.871, well, that's because steel has a modulus of elasticity that's, 8 times that of concrete. So it's just something to keep in mind.
So because it was concrete, that's going to be like,
Well, theoretically, yeah. The only thing is this. You got to be careful with that. Let's put it like this. It's not going to be 8. You might have some situation where you've got 4 KSI concrete in the slab and 8 KSI concrete, let's say, in the beams. It's not going to cause a difference of, a factor of 8. But remember, FC prime changes what your modulus of elasticity is, which is going to change what your N value is. So if you go through and do the math, it's not going to be 8, but it might be a little larger than 1. So it's just something to keep in mind. So, yeah.
I'm not sure if you've seen it or drove across it or not, but do you know where I think it's a dam, lock dam somewhere on the canal, close to Portable. There's like a
Marmet?
yeah, yeah.
I know where it is.
Like a bridge that right in the center of it, there's a huge beam that comes out, and then there's like piers sticking down. I don't know what is that?
Are you talking about?
Yeah.
it's much wider than the.
Yeah.
So it's kind. I think I know what you're talking about. It's kind of like an integral pier cap in a way. So you've got like here's your cross section, and then you've got that. But then at the pier, you've got this massive beam like that, and then there's piers that go down, kind of like that. Is that what you're talking about? I'll tell you, it's kind of interesting. It's a way really to get around clearance requirements. So instead of a hip bone connected to the leg bone type philosophy, girder sits on the pier cap sits on the pier sits in the ground. Instead of that, you're actually creating what's called an integral pier cap. In this case, it's a steel pier cap where the girders actually frame into this massive box section, and then that goes into the piers. The advantage of it is that instead of having your pier cap sit below the pier or sit below the girders, it's sitting right here, so you get more room under the bridge. There was an expansion of, I'm trying to remember where it is. It was around the Richmond area, the massive interstate expansion. I think it was Richmond. Don't quote me on that. But the interstate corridor through the Richmond area, they did a lot of expansion, and those bridges were all over the place mostly because of clearance issues. So they're pretty nifty though. But the actual box section has some very interesting design because it's not a very long thing. I mean, this red part, that's a beam like any other, okay? But the thing is, it's not a very long beam, but it is subjected to phenomenal amounts of shear. Yes, oh yes, because it's in that small space, you've got a lot of shear, because the whole damn bridge is sitting on that. You've got a lot of shear and a lot of moment in that particular location, so it gets kind of interesting. That one transfer beam is far larger than the main girders of the bridge. So, so yeah. How old is that bridge?
Fairly new. I just didn't know if there was any more pros to adding that besides
Clearance.
I've only seen one of those.
I also don't want to give you an always and never answer. When you've got really complex geometry, there is a perception that you can get tighter clearance and tighter tolerances if you go with steel versus concrete. So I don't know that that's always the case, but I know that in complex geometry situations, curved bridges and things like that. So I would say that there's probably a little bit of that going on, a little bit. So I kind of know the bridge you're talking about, but I don't know specifically.
I'm sure if it's always been like that, and I think they redone it at some point. But that huge box thing, whatever you want to call it,
Okay. It's probably a clearance thing. It might, if they were doing rehab and retrofit, it might have been easier to do that than completely replace the pier altogether. If all you have, two smaller pier sections, it might be easier to do that than drive one big one right in the middle of the road, or right in the middle of all that traffic under there. So I was wondering that. I know we're going off lecture here for a second, but what is going on? We're civil engineers. We can look at the crane. So
If you look down there, there's a motor.
Is it for the elevators or not elevators? Small field, maybe for HVAC or? Oh, it's one big hunk of metal. I mean, yeah. Although that crane does, it looks like overkill, but it might deceptively not be overkill. If that's all it's lifting, though. Yeah, there's a, for those of you who didn't look, there's a motor there. And I'd say the motor is about as big as this. Is it maybe smaller? No, yeah, so. And then there's, yeah, they've got 2 lanes, a 3rd Avenue blocked. And I don't know. Okay. Here, the cartoon whistle, the oh. Tom and Jerry. That's bringing it back. That's bringing it back. Okay. Let's get back to some distribution factors. Everybody good so far? Okay. I want to go back to the spec so that you see what I'm doing specifically, because I know I threw a lot of tech at you last time. So let me. I'm in chapter, well, I want to be in chapter 4. That's chapter 5. Come on. I know it's been a while since you've seen these, right? Oh, of course it freezes. Well, there's effective length factors. Oh, there we go. Okay. All right. So the first thing that we do is we identify our cross-section. So we're obviously dealing with cross-section A, right? Steel beam, concrete deck. And we go through our tables, and we go through them one at a time. So the first one is moment in interior beams. Okay. So let's see. So go through, start going down the list. Cross-section A, concrete deck on, or reinforced concrete on slab or steel or concrete beams. So this is obviously going to be our case. Let's look at our range of applicability. Does our girder spacing fall within this range? Yeah, I mean, it's 10. Does our span length fall within the range? Our slab thickness, number of beams. What about kg? We got a kg of what? 500,000 something? That falls within the range. So here are our distribution factors. Now, these are for moment and for interior beams only. So all right, so moment. Okay. So our distribution factor for one lane loaded scenarios is this. Now these are exponents, just a heads up. Okay. So I'm going to leave units off just for brevity because the units have already been factored into the equation. So 0.06 plus 10 over 14 to the 0.4, 10 over 90 to the 0.3, and then 509,871 over 12 times 90 times 8 cubed, 0.1. I'm going to give you all a second. Let's see what you can come up with. You all can do calcs. I'm going to see what's going on outside. Now they're lifting some panels. This might seem like a futile exercise, like example problem graduate class before, and everybody, like, because of the exponents and the size of the equation, it can get a little funky. So you have an answer? 0.51. Okay, that kind of sounds right. Well, give me 3 decimal places. Yeah, that sounds pretty good. Okay, so let me explain what this means, okay, because I really want everybody to understand this. So what I would do, let's say this is the only distribution factor I computed at all, period, okay? What I would do is I'd go to my structural analysis textbook and I'd do my influence line analysis and I'd put my moments in, or put my trucks on there and get my moments and shears, right? When I'm looking at moments, what I would do is I'd take whatever moments I get from what I learned in structural analysis and I'd multiply them by 0.508. And what that would do is that would tell me how much moment I need to analyze that or design that girder for. Does that make sense? That's what these values are, okay? Now that's a 1-lane loaded scenario. 2-lane loaded scenarios are, I can't believe I remember these. It's 9.5. That's S. That's not 5. What's that? Well, I'll be honest, it's where my master's thesis was on this. Like, these are the ones that have been, like, burned into my memory. Now, I think I got the exponents right on that one. See, my master's thesis was on 1-lane loaded scenarios, so those are the ones I really remember. And it was on moment, so that's what my topic was. So I'm not going to do the numbers. You all can probably recall that in your calculator and just change a couple constants. So. Say it again. 0.734. Goodness, pen got away from me. Everybody okay with that? So I know the equations are a little funky, so it's just something to keep in mind. Okay, so these are moment interior beam distribution factors. Now our next one that's in the code, let's see, take it down the line. Moment exterior beams, okay? And this is where the lever rule comes into play. So let me explain how the lever rule works. Okay, So I'm actually just going to do a lever rule analysis. Right now. Now, if there's one thing I would change about this bridge, it would be the width of the barrier. I don't really like it, and you're going to see why right now. Okay. Now, this barrier is 18 inches wide. Okay. Now, when you perform a lever rule analysis, what you're trying to do is you're trying to maximize the effect of the girder of interest. Now, what we're going to be using the lever rule for is for exterior beams, so the ones on the outside. So if I want to, worst case scenario on those beams, I'm going to take that truck and I'm going to shove it as far over exterior as I can. The farther I push this truck towards the barrier, the worse the effect is on this exterior beam. Now, the code stipulates that the closest a truck can be placed for analysis purposes is such that, I've got one load here and one load here. So this is half the truck. This is half the truck. The code stipulates that this distance here shall be no less than 2 feet or 24 inches. Everybody okay with that? Okay. Now, pop quiz, what is this distance? See if everybody remembers that. Huh? It's not 8. 6 feet or 72 inches. All right. The distance between your axles on the truck is 6 feet. Okay. Now here's the reason I don't like this bridge. Okay. Does anybody remember what the overhang is? 3'6", right? What is 3'6" in inches? 42, right? Okay. What's 18 plus 24? 42. It's 42. Yeah. That is an absolute complete coincidence. Okay? It is a complete coincidence that this roller happens to be right under that wheel. Complete coincidence. Okay? This dimension is 42 inches. Now, what's the girder spacing? 10 foot? Okay. So our next girder is somewhere like out here. So the way we sort of draw that is we do this, something like that. And this dimension is 120 inches. The question that we're asking is based on this scenario, what is that reaction? Okay? So I propose that if you sum moments right there, you can determine what that reaction is pretty easily. So sum moments. Y'all remember this, right? So, summing moments at the hinge, what do I have? I have R times 120 going like that. All right? So we'll have R times 120. That's the closest. It can't be right up on it. Well, two reasons. One, and this is going to seem like a cop-out, but it really is just a code specification. But two, we are talking, let's just look at physical trucks. There is a difference between the center line of the wheel and where the edge of the truck is. You see what I mean? It's the wheel, the center line of the wheel does not occur right along the edge of the truck. There's a space. You can just pull up any image and see that. So. Yes, exactly, yeah. Make sense? I mean, even if the truck was like driving along the bridge and like sparks were flying because it was rubbing right up against the barrier, bless you, rubbing right up against the barrier. The point of contact with the barrier and where the center line of the wheel is, there's a gap. So, make sense? All right, so we have R times 120. What do we have going in the opposite direction? We have 1/2. And how far is this point from this point? That is a complete coincidence, but it's exactly right. Really keep that in mind. So this happens to be 120. And I'm even going to write this down. All right. What about the other 1/2? What's its moment arm? 48. Now, how'd you get that? There you go. So, do I need to go through all this, or can you just tell me what R is? Say it again? 20, that doesn't make sense. If the loads are 1/2, yeah. 0.7. Yeah, that sounds right. That it's 0.7. Does that make sense? Okay. So far, so good? Okay. Now, if you open up the code and it says, okay, what's the distribution factor? It says a lever rule, right? So is our distribution factor 0.7? No, it's not. The reason why is this. Okay, and I'm going to pull up the notes. All right. Once the lever rule has been employed, we have to adjust those by multi-presence factors. And I mentioned these near the very end of the lecture last time. But multiple presence factors account for the probability of coincident truck loadings. Like if you have a truck in the worst case scenario at a particular location on the bridge, what's the probability that there's load in the other lane? If you have, if you've got a 2 or 3 lane bridge and you only have 1 lane loaded, well, what's the probability that there's load in the other lane? It's pretty high. But if you've got 3 lanes loaded simultaneously, what's the probability of that occurring? Well, it's pretty low. So let's go back to our discussion. We're looking at moment in exterior beams. Okay, 1 lane loaded scenario is said to use the lever rule. So what I'm going to do is I'm going to take the lever rule, and since it's a 1 lane loaded scenario, what am I going to multiply it by? 1.2. Okay, so just to keep that in mind. All right, so open up the spec, distribution factor, moment, exterior beams, 1 design lane loaded, lever rule. So go into here. So our 1 lane loaded scenario is that. And that's it. That's your 1 lane loaded scenario. Your 2 lane loaded scenario, let's look right here. So 1 lane loaded scenario, lever rule. 2 lane loaded scenario. We've got something a little interesting. What we do is we take the distribution factor for the interior beam and we adjust it by this following factor. So let's take a look at that. So we take some adjustment factor times this. Now, first off, that adjustment factor is 0.7 plus DE over 9.1. Okay? Everybody see where I'm getting that? Just right there. Now this one's an easy one. For the interior girder, we have two distribution factors that we can use, 0.508 or 0.734. Which one do we use? Worst case scenario. So far, so good? Not too bad, right? Okay. Okay. The only thing that is of confusion is this DE. DE is the distance from the center line of the exterior beam to the edge of the barrier or the curb. And it's in feet. So you tell me, what is that distance going to be for this bridge? From the edge of the barrier to the center of the beam in feet. 2 feet, right? We're going from edge, so it's 2 feet. So that's 2 feet. So what is that? That's an easy one. .675. Do I have a second on that? So now we haven't talked about special analysis yet, and I'll put that to the side. Let me ask you a question. If you were designing beams for, what's your worst case distribution factor? For 0.84. The 0.84, this one was even larger than the interior beams, right? So what I would do is, if I was a designer for a bridge like this, I would say, well, let's just design all the beams using a distribution factor of 0.84, and then we'll just use that same beam everywhere. It's a lot easier, okay? Good? Okay, it's 9:46. I think I'm going to call it. We'll look at shear next time. Shear's a lot easier. It will go by quick. What isn't going to go by quick is special analysis. That one's a little unique. It's basically loads on pile groups, but we will handle that on Wednesday. After that, I don't want to keep harping on this, but I really want you all to think about what it is you need to cover from here on out to get you moving towards your project. Because what I've tried to do is cover the stuff that I think would be really difficult to figure out independently, but we are getting to a point where it's a big road trip, and it's time for you all to take the wheel. So, sound good? All right, that's all I've got. I will see you all. I'll see you all on Wednesday.